I would like to come back to the action principle. The Lagrange formulation was based on the observation that there is a functional, a specific functional, which we call the action, which is extremized in classical mechanics. So we started out from the observation that the equations of motion of classical mechanics are equivalent to the requirement that this action functional is extremal. And this action functional was defined in configuration space. So it was defined in the space, in the f-dimensional space, with coordinates qk. What I would like to show is that the extremization of the action functional also works in phase space. So not just in configuration space, but also in phase space. So in the Lagrange formulation, we had the following picture. We looked at trajectories q of t. So this axis here, this vertical axis, I can only draw it in for the one-dimensional case where we have a single coordinate q, and this vertical axis represents configuration space. And what was the action principle in the Lagrangian case? We said we fix at some initial time, we fix the configuration, we fix all the q's. We also fix the configuration at some final time. And then in between, we allow arbitrary trajectories. So these start point and end point are fixed. In between, we have some trajectory q of t. We allow arbitrary trajectories in between these two endpoints, and the physical trajectory is the one which extremizes the action functional. We can look at other trajectories, that alternative trajectories that are not the physical trajectory, and they differ from the physical trajectory by some delta q of t. That was the picture in the Lagrange, and actually that was the starting point of the Lagrange formalism. Now we'd like to extend this to phase space. And for that purpose, I have to try to draw this in 2 dimensions, in 3 dimensions. I'll make it a 3D plot. So again, from left to right, we have time. And then we have q and p. So we have, in a way, we have perpendicular to the time axis, we have phase space. So in this picture, we have phase space spanned by q and p, and then we have, from left to right, we have a time axis. And now we do the same as above. We say we have some initial time t1. At this initial time t1, we fix the position. Let's say it's q1. Now that's the same as above. We fix the position at time t1. However, now we have an extra dimension, which is the momentum. And we allow arbitrary initial momenta. So the allowed initial states are all states that lie on this green line. These are the allowed initial states. All states on this thick green line are allowed initial states. We do the same for the final time. We have some time t2, which is our final time. And also for t2, we fix the position q2, but we allow arbitrary momenta for the final state. So here too, we have this thick purple line, and these are my allowed final states. So again, Q is given, but the P's are free. P is free. So what are the allowed trajectories? Let's say the physical trajectory is the red one, this one here. Let's say that this is the physical trajectory. But we could have, so when we look at variations of that trajectory, and we could have another trajectory that looks like this. So the blue trajectory is an allowed trajectory. It has the same initial position and the same final position, but it has a different initial momentum and a different final momentum. And also in between, at some intermediate time, it may differ from the physical trajectory both in position and in momentum. And we can vary them independently. Now you might say that when I vary the q of t, the position as a function of time, I vary the trajectory in configuration space, then this corresponds to a certain variation of velocity, and this determines the variation of momentum. But this argument already presupposes the relationship between velocity and momentum, which you only have for the physical trajectory. But here we allow arbitrary trajectories, so we do not assume a specific relationship between q dot and p. Now, p is really an independent variable here that we can vary independently of q. So this is the picture. The question is, in the Lagrange formulation, we know of all the trajectories between the fixed endpoints, the physical trajectory is the one that extremizes the action. Now we want to understand if in the phase-space picture below, where we allow more freedom, we allow many more trajectories, we ask whether it's still the case that the physical trajectory is the one that extremizes the action. It turns out that it is. And this is the calculation that I want to show you on the following page. What is the action? It's still given by the integral from initial time to final time, dt, of the Lagrange function. But the action is now considered as a functionale, not on a trajectory or in a functional configuration space, but it's a functionale of the trajectory in phase space. So the action depends on q of t, both q of t and p of t. Yeah? It has become a functional that depends on two functions, q of t and p of t. The trajectory is now in phase space rather than configuration space. Now we do the following. We had, up to this point, we always expressed the Hamilton function with the help, or we defined it with the help of the Lagrange function. Now we do it the other way around. We write the Lagrange function in terms of the Hamilton function. And we say this integral, t1 to t2 dt, over the Lagrange function, we write the latter as sum over I pi qi dot minus the Hamilton function. Here another important remark. You might say, okay, we have here qi dot, and we have everything in phase space, so we would like to replace the qi dot by pi. We'd like to express the qi dot in terms of the q's and the p's, but this we cannot do here yet, because we are talking about arbitrary trajectories in phase space. So the relationship between velocities and momenta do not necessarily hold. No, this relationship only holds for physical trajectories. So we cannot simply express qi dot with the help of momenta. That's where we stand, and now we have to look at the variation of that functional. As we assume we are here, we start from the physical trajectory. Now we deviate from this physical trajectory, both and independently, in the q direction, in the p direction, and we look at what variation of the action that entails. So we look at the variation of s as we vary q and p. Now we look at all the terms in the integrand independently, and where we have a product, we have to use the product rule. So pi qi dot, if I vary that, if I vary both p and q infinitesimally, then I get a contribution p and variation of q dot, and I get a contribution q dot variation of p. For simplicity, I do this in the 1D case, so I drop all the indices of the p's and q's. Yeah? So that's the variation of p, q dot, these two contributions. Then we have the variation of the Hamilton function, and that gives us two contributions. The Hamilton function in turn depends on q and p. So if we vary p, then we get the contribution partial h over p, variation of p. If instead we vary q, we get partial Hamilton function over q times variation of q. Now let's focus specifically on the contribution that comes from p times variation of q dot. This contributes to the integral in this form, t1, t2, dt, p times variation of q dot, which is the time derivative of the variation of q. So we have in the time integral, we have momentum times a time derivative. We can do partial integration. We can say this is p times delta q in the limits t1, t2 minus integral t1, t2 dt, and then we have the time derivative on the p. It gives p dot delta q. We had fixed the boundary conditions for q at the initial and the final time. So this here is equal to 0, because at the boundaries the position is not allowed to vary. Yeah? This is by boundary conditions. We are left with the second integral, so minus integral t1, t2 dt p dot variation of q. Let's insert that into our expression for the variation of the action. We have integral t1, t2 dt. Let me also do just a little rearrangement of the terms. Let me group all terms that are proportional to the variation of p. We have, in the integrand, we have a q dot variation delta p. So I have q dot times variation of p. And then later in the integrand, we have a minus partial dh over dp times delta p. So let me take these two together. And then let me look at the terms that contain a delta q. And there we have, in the integrand, we have a minus partial dh over dq times delta q. And then we have the blue term, which was originally p times delta q dot, but which by partial integration we show to be minus p dot times delta q. So we have a delta q there as well. And also with the minus sign in front. So let me take the minus sign in front of the bracket, and then we have inside, we have a p dot plus partial dh over dq, and all of this is times variation of q. That's the variation of the action. What happens when we have the physical trajectory? When we are on the physical trajectory, then the equations of motion are satisfied. The equations of motion in the Hamilton formalism are q dot equals dh over dp, and p dot equals minus dh over dq. So on the physical trajectory, by the Hamilton equation, this is 0, and that is 0. These two round brackets are 0 by the Hamilton equations. So we find that when we are on the physical trajectory, the integrand of the action, or the integrand here, vanishes by virtue of the equation of the Hamilton equations. So we find that on the physical trajectory, the variation of the action is equal to 0. And therefore, indeed, on the physical trajectory, the action reaches an extremum. This also has a name, the fact that the physical trajectory extremizes the action. It's also known as the Hamilton principle.